Hello, I'm James Burnett, and I'm going to be going over Lab 2, which is the charge tape labs, but this time treating it like lines of charge. So previously, we assumed that each piece of tape was a point charge. But now we're going to advance our model to be more accurate and treat them like lines of distributed charge. Some properties are still going to be the same, mainly with the actual sign of the charge on each piece of tape being positive. And then we're going to use our model to observe how the charge changes from treating like a point charge to a line of charge. So some physics concepts you need to be comfortable with is the law of attraction. Basically, just know that if two pieces of tape have the same charge, they're going to be repelled. If they have opposite charges, they're going to attract. Then we need to be comfortable with Newton's second law and basically just summing forces to try and get them to be equal to zero. And the only two forces on this are going to be the electric force and the gravitational force. Lastly, you need to be comfortable with Coulomb's law. We do have some assumptions to make for this lab. Mainly that each U-tape is going to have the same charge magnitude. Secondly, each piece of tape is going to have a uniform charge distribution. And lastly, the force of air resistance is going to be negligible on the system. It's a very similar setup to what we did previously. And what you're going to do is take a piece of tape and stick it onto the table, and that's going to be your base tape. Then you're going to fold a little bit of tape underneath, and then that's going to be your U-tape. Put the sticky side on top of the base tape and rip it up, and now you have a charged piece of tape. Go ahead and confirm that it's going to be a positive charge by rubbing a pen with a cloth, and then go ahead and see if it attracts. It should, in which case, you know it's a positive charge. Lastly, we're going to be doing the same setup for the hovering tape condition, in which case you're going to have two pieces of charged tape, one elevated and put on two pieces of book, and then you're going to go ahead and take another piece of charge tape and just bring it closer up until the point where it starts to levitate, and then find the distance between that. Alright, so we do have some calculations to go over, but it's nothing that you can't handle. So we do have a couple knowns. Firstly, the mass of the tape came out to be 0.0002 kilograms, the length of tape being 0.2 meters, the distance between each tape when it began to levitate was 0.03. So we're going to take those values and go ahead and find the forces on it, and the charge. And to do that, we're going to take gravitational force, which is just mass times gravity, and then we get 0.00196 in the negative y direction. And then we know that the electric force, following Newton's second law, and that the net force comes out to be zero, has to be equal and opposite to the gravitational force. So it's the same magnitude, but this time in the opposite direction. Then we're going to take Coulomb's law, and we're going to go ahead and rearrange it to find Q. And once we go ahead and plug in all of our values, you see that I got 1.4 e to the negative 8. And that's just going to be important for kind of some analysis. We're going to quickly compare Lab 1 code to Lab 2 code. On the left is my Lab 1 code, where we treat them at point charges, and as you can see, the first two lines talking about the actual forces, the gravitational force and the electric force, are equal, but they're in opposite directions. And if we look at the actual charge calculation, you see that it's basically what we previously calculated. But now we're going to take that value, and we're going to put it into our new sample code and our new lab code for Lab 2. And you can see that the electric force is significantly smaller than the magnitude of the gravitational force. Now what this means is that we need to actually change our charge. And how we're going to do that is by trial and error. And so in the top left, you can see that I had the point charge stored and the real charge. And the real charge came out to be 2.86945 e negative 8. And we're just going to observe how that looks in a little bit. But you also need to have your own E field calculation, and mine is in the bottom left. And then lastly, how we're actually calculating the total electric force is we're treating this line of charge as basically a collection of point charges. So you're going to have some differential, just small point charge, and that's going to be interacting with everything else, and you're going to get a force. But you're going to go ahead and sum all those forces just from each individual point charge, and then once you sum up all of them, then you're going to go ahead and have the new net force acting on it. So you may be wondering what it looks like if everything goes perfectly. And that's going to be this. As you can see, the magnitude of the electric force and the gravitational force are the same. The white arrow is the electric force, the yellow arrow is the gravitational force, and the green arrows are the small components of the electric force. It's for each point charge there, and basically observing how every other point charge on the blue side is interacting with the red. Now, we do have some final questions we need to go over really quickly. What would have happened if we treated it like a point charge? Well, first of all, our charge for a line is 2 times greater than our charge for a point charge. So as you can see, that's a very big difference, and it's just not really accurate just by the geometry of it. But you may be wondering why these estimates actually differ and which one is likely to be closer to the real value. And that's because previously we were assuming that everything is just concentrated to one singular point, whereas it's actually distributed across the entire surface area of the tape. And that's far more important. That's far more important and realistic in an actual setting, in like a lab setting. So yeah, overall, thank you. I hope you guys have a good day.